Welcome back. Today will be the last of our lectures. So I think we finished up with nuclear medicine last time. So that leaves us with nuclear power and nuclear weapons to talk about today. And we'll go ahead and do that a little bit later on. The first thing we're going to do is take our last quiz as promised for today. So we'll do that in a minute. But first, I just want to make one more announcement. At the very beginning of the term, I gave the option for extra credit if you took notes throughout the semester and you kept a set of notes and so forth. I just want to remind everyone of that. Don't go back and try and make notes or anything like that. I guess you could if you wanted. But if you have been keeping up with notes and so forth and you have a set that you want to submit, and remember, when you give them to me, the reason I'm doing this is to make them available to other students later on. I won't sell them or anything. Apparently there's like a website you can sell your notes on now. I had no idea there was such a thing. But apparently there is. Feel free to do it yourself if you want. But that's why I'm doing it, and since you're helping other students, I give extra credit for it. Now, I don't want to take those notes before the final, because obviously I hope that you're using them to study and so forth for the final. So I just want to tell everyone that what I'll be doing is collecting them on that day. If you want to make a copy of your notes so you can keep the originals, that's perfectly fine. You can hand in the originals to me and I will copy them, and then you can pick them up. Well, you can pick them up anytime, like after a week later, but I guess next term, stop by my office and pick them up and so forth as well, so you can get those back. If you don't want them back, I'll be a little sad on the inside, but I understand. They'll just be in my office for like a year and a half until I get rid of them. Okay. Does that make sense? Yeah.
How many do you take to determine who's there?
Okay, so everyone gets 1%. The best set, I'm 99% sure, and that's not decided by me, it's decided by people I grab and pull in my office, gets 3%, and then the second best gets 2%. So everyone's guaranteed a 1% bump on their final grade that does it with a complete set. I mean, don't hand in like 5 pages and call it a complete set. 1%, and then the select one, the couple of best, would be 2 and 3. If that makes sense. Yeah, and I obviously don't vote in the 2 or 3 because I know the students and I don't want that to influence pro or con. So it's kind of a blind vote. But if you have your set of notes anyway that you've been using, you may as well, and you're willing to share them with other students, then you may as well turn them in and get your points for them. Okay, that's my philosophy anyway. Okay, any questions about anything right now?
What day is the exam again?
The exam,
Thursday.
Okay.
It's the 15th.
No, the next exam is.
oh yeah.
Oh, the final or the exam?
Oh, yeah, the final.
15th.
Okay.
Okay, there we go.
So wait, how comes our last lecture we have Tuesday and Thursday?
Okay, so Tuesday we have our last chapter exam, and then Thursday I will give that back. We will go over it and then simply review for the final. So we won't have any more, better way probably to say is we won't have any more new information after today. Anything else right now? Okay, so let's get this quiz out of the way. I don't know that you need a calculator, but if you do, please feel free to use your phones and so forth. If you don't have one, just an honor code thing, don't cheat. I'll come down there. background. Okay, just so everyone is familiar, the word, the background, a background source would be something that is a radiation source you're exposed to, but not man-made, like always around. It's just present. If that makes sense. Say 2 more minutes. Is everyone finished? Okay, well, if you're finished, let's pass them to the end of the rows, and I'll come around and grab them. Doesn't really matter which direction they go. I'll walk both of them in the end anyway. Thank you. Okay, so this quiz was originally meant for last week, so it covers pretty much the beginning of the chapter. And just running through the questions really quick. Background radiation then is radiation all around us, so in this question, there's literally hundreds and hundreds of both types. But a few background ones could be the cement in the buildings, it could be the people around us, it could be the sun, it could be, I don't know, it could be just about radon is a good background one. I mean, there's a lot of different ones there as well. Now the man-made ones, those would be man-made ones. The most common would be smoke detectors, microwaves, power plants is on this one. That's a good answer, power plants, those types of things. So it'll just kind of have to depend on what you wrote. Yeah. Would you say that be man-made or background?
Background.
Background, yes, I would accept it. I'd probably take it as man-made too, because I guess we move them and so forth. But yeah, banana is perfectly good. As a matter of fact, that's probably one of the bigger sources that we are exposed to. I should have mentioned that one. Okay. Number 2, the following nuclear equation. I wrote it up here on the board. Now, when you're doing nuclear equations, the thing you have to remember is the numbers on one side of the arrow have to be equal to the numbers on the other side. So we have 115 here, and we've accounted for 0. So that means we're going to have 115 still. We have 47 and a -1. So this is going to be 48. 48 plus a -1 is equal to 47. And I chose this one specifically to trip some students up and remind them that you need to be careful with the minus there. So hopefully you caught that when we were doing it. And then finally, the element is going to be CD. Questions about that? Yeah.
On the test itself, how many more steps will we have, or would it just be questions just like that? I mean, obviously there could be different, alpha, beta, and gamma different ones, but I mean, does it get any other additional steps included?
Not really.
Okay.
No. So basically, all of the questions come down to the fact that 2 out of the 3 are given to you, and then you figure out what the third is. So, so that's the answer to the quiz, but it could have been something like this. And then you would find the beta, or the question could say what type of radiation is given off by this. And 48's not right?
I was trying to see how you got.
Oh, right here. So you start out with 47 as your atomic number, and then you add 1 more because of the negative, so that goes to 48, and then it's just CD there. And I could say what type of radiation is given off here, and then you would have to find it, recognize that it's beta, and write beta. That would be the most complex version. Yeah.
So we won't have one, like, on the homework assignment, it gives us an isotope and then it tells us, it loses a beta, gains, it's like 3 steps where you have to do beta, then 2 decas.
Yeah, no, you won't have that on the exam. I don't feel bad about that on the homework because you've got the time and the book and stuff, but on an exam, the basic idea is, can you figure out the numbers have to be the same, and I can do that with this type of problem, not with a multi-step. Yeah. And I don't plan on having to give off 2 types of radiation or anything like that on the exam either. So, yep. Okay, so we good with that? We can do a few more later at the end of the class when we review, if you want a couple different ones and so forth. But I think I kind of pounded that in enough at this point. Then finally, how long has passed if an isotope with a half-life of 2 days has decayed to 25% remaining? Well, the first thing you need to do is start with 100%. And after 1 half-life, that's going to decay to 50%. After 2 half-lives, it's going to be 25%. So 2 half-lives have passed. If each half-life is 2 days, 2 days times 2 is going to be 4 days. 4 days has So you find how many half-lives, you know how long each half-life is, so it's a multiplication to figure it out. Yeah.
I'm sorry, in the first question, so the background radiation, it couldn't have been alpha, gamma, or,
No, because alpha, beta, and gamma are types of radiation, and that is not specific to man-made or background. Like you have beta that's man-made, and you have beta that's background. You have alpha that's both, gamma that's both.
when you say background, do you mean like, well, like nature, like non-man-made?
Non-man-made.
I thought you meant.
So, so it's called background if it's just constantly around us all the time, and so forth. Other questions? Yeah.
A quick question for the last question. What are the atoms again for the half-life? Like, what was the actual question?
Oh, okay. How long has passed if an isotope with a half-life of 2 days has decayed to 25% remaining? So you need to see how many half-lives have passed, which would be 2, and then each half-life's 2 days. So that would give you, 4 days total. Cool? Okay. Any other questions there? Now, looking at the exam, from my point of view, there's not been that much information given in this course, so it's only been over 1 chapter, for example. So, you know, things like this, where the previous one there may have been 1 question about it, I'm going to have 2, maybe even 3 questions, so that if you mess up on 1, it doesn't trip up your score. Like if I had 1 question for each topic, there would be like 6 questions on the exam. So I'll make like 3 questions of each, and then that way if you just make a simple mistake, you're okay, but expect that, okay, when you're going through it. Expect that there are going to be repeats in terms of these types of things. So for this example here, writing out a nuclear equation or using a nuclear equation, I would say there are probably going to be between like 3 and 5 questions about that. A half-life, there'll be 2 or 3 questions about things like that. And we'll run through the topics at the end of class as well. And literally, it'll just kind of be a list almost for you in terms of these things. Some of the information stuff, like we're talking about now, it's a bit more open-ended. But in terms of half-life and equations and so forth, it's pretty much all there is. Okay. Any other questions before we get started on lecture material today? Okay. So what we're going to do then is we are going to talk about nuclear power and nuclear weapons. And again, I've said this time and time again, and I'll keep saying it. These are basically the same things. The only real difference between a nuclear power plant's energy and a nuclear weapon is a nuclear weapon's energy is released all at once, where a nuclear power plant, they control the release of energy. As a matter of fact, in a power plant, when they lose control of that energy release, that's when you have a meltdown that occurs. Okay? And then you basically have a nuclear bomb going off in your power plant. So when we're talking about these, they're really the same thing. Iran wanted to be able to create enriched uranium for nuclear power for their citizens. The United States and other countries said, yeah, we don't want you doing that. So what we're doing instead is we made the nuclear deal with them, and they are buying uranium from Russia and then using that in their development of nuclear power plants and so forth. But this idea of being able to make your own fuel for nuclear reactions is one of the most highly, controversial and controlled secrets in the world. North Korea. North Korea has recently developed nuclear weapons, it's believed. So that's going to change the world as we know it, actually, whether we like it or not. And this all starts out with nuclear fission. So nuclear fission is where you take a large atom and break it into smaller fragments. in terms of nuclear power and nuclear weapons, the two examples of these large atoms that are generally used is uranium-235, which is element 92 on the periodic table. And that reaction is shown up here on the board, and then plutonium. Plutonium is the other one that's used. It's not used as much as uranium, so you don't hear about it nearly as often, but you can do the same basic principles with plutonium as you do with uranium. It's just a different source. Now, when you have a nuclear reaction, what you're doing is basically you're taking a neutron and reacting it with uranium-235 to create uranium-236. Uranium-236 is unstable and it breaks apart. Now when it breaks apart, you're going to make some daughter particles, and then you're going to release a couple neutrons and energy. When this occurs, something very, very unusual happens. And this unusual thing that happens is matter is changed into energy directly. So you have some sort of mass, and when this reaction occurs, that mass is changed into energy. Now to describe this, we have probably the most famous of all scientific formulas, E equals mc squared. Okay, this was postulated by Albert Einstein, I guess almost 100 years ago. And he came up with this equation before we had nuclear bombs and nuclear weapons and so forth. But what it basically says is energy is related to mass, and then c is the speed of light. Now mass that's converted is actually really, really small. It's a very small amount of mass that's actually converted into energy. Chemists generally, like when we're doing our equations and so forth, we ignore it. It's so small. We don't worry about that. We just know that it's happening. But even though you have a small mass, you've got the speed of light. Speed of light's a very large number, and then all of a sudden you're doubling it. So if you've got a very large number times a very large number, it very quickly becomes a huge number. Okay? And that's the idea here. Even though the mass is small, the c squared is so large that you get a significant amount of energy out of it. Now, if you just did this with one atom, that amount of energy wouldn't be anything to write home about. But what particularly makes this a destructive force in terms of weapons and a large energy source is the idea here of these neutrons released. So you've got this reaction that occurs. You're creating daughter particles. These are your nuclear waste that you're going to have to deal with at some point. You're creating energy, and then you're also releasing neutrons out of here. This is important because those neutrons can then go and react with more uranium atoms. So the whole thing started by a neutron hitting uranium. So if you have that occurring, you're creating this uranium-236 breaking apart, and neutrons are coming out. These neutrons can then run into another uranium atom. So if you start with 1 and say 3 neutrons come out, then you've got 3 after one atom breaks apart. After the next series of atoms break apart, you've got 9 going on at once. Then you've got 27 going on, and then so forth and so on. And very quickly you get to a huge number of these atoms occurring all at once. So we've got to go back and think about atoms. When I've got say, heaven forbid, hold a pile of uranium in my hand. That's not 10 atoms to react there, right? That's billions and billions and billions and billions of atoms all at once. So if there's nothing for these neutrons to run into besides uranium atoms, you don't have 5 of these going on at one time. You have millions and billions of these reactions going on at once. So even though the individual atom's energy release is small in comparison, by the time you have billions of them going on at the same time, you end up with this astronomically large amount of energy that's released. And that process of the neutrons breaking free and then going in is what's called a chain reaction. It's where the product of your reaction can then go and start another reaction as it's going on. And this is exactly what happens in a nuclear reaction. Does that make sense?
So will we need to know that equation that was on?
No.
Okay.
Nope. No, it's good. It is a good nuclear equation. Like if you add up the numbers and stuff. Actually, why is it? I think there's an extra neutron there for some reason. But the general principle's there, but you're not going to need to know it or anything like that. And to be honest, that's not the only way they break apart. That's the most common way uranium breaks apart, but there are other things that can happen as well. And those daughter particles can break apart to other things and so on. It's just a big mess. Yeah.
When radiation's used, obviously you're taking an element that's already known, and it's obviously going to continue to break down to other known elements. Has anything ever happened strange where something's broken down and it's not something that's known?
Well, you don't see that with fission because you're going to smaller. And if you start with uranium and plutonium, we know all of the elements going smaller. I mean, you can't have half of a proton,
Right.
so it falls in one. Now, there is also fusion, which we'll talk about right at the end of it, where you're combining things together. And there they take them and they combine them together and they're making things bigger. So if you start with uranium, for example, you could absolutely get to things that are bigger than 118. And that's how we end up finding new elements. Just the other day, or yesterday even maybe, the official names of 4 of these elements were released. And they were all made that way, by taking and combining stuff together and then watching what comes out.
Okay. But the opposite way, obviously, you can't. There's a limit to how far you can go.
Yeah, generally, yeah, there's a limit, and everything lower is known, so there's not really much else to find there as you're going through it. So this chain reaction really is the key to understanding what's going on and where all this energy is coming from, because this is happening over and over and over again. Now, to control it and to slow the reaction down, what you need to do is you need the neutrons to run into something other than uranium-235. So if they run into anything other than uranium-235, it stops that neutron's path. Okay? It doesn't create more and so forth. So to control what the rate at which these are, especially in nuclear power plants, what they use is what's called cooling rods. And cooling rods are materials that absorb neutrons. So let's say, for example, we've got one going in, and then we absorb 2 of our neutrons so that only 1 reacts. Well, that's still a 1-to-1 ratio there. You're not getting a buildup of that. And then from there, you can get 1 coming out again. Say we absorb this one, and only 1 as well. And you can control your reaction that way. So to control reactions in nuclear power plants, what they do is they use cooling rods, and they absorb neutrons, or they leave other things in the uranium. The uranium used in power plants, I think, is around 20% pure, where the uranium used in a nuclear weapon is 90% pure. Because they want that reaction to go very, very quickly in a weapon, where in an actual power plant, you're going to slow it down anyway, so there's no reason to make it as pure to start with. Purifying uranium, you guys have all heard this term before, is called enriching uranium. Enriching is what the terminology is for purifying. So you start with like a couple percent, and then if you want weapons, you enrich it until you get to about 90% pure. Power plants doesn't get as high. I think it's like 20%. Yeah.
It says uranium-235,
Yep.
but it was uranium-236. Does that matter when it's causing more reactions?
No.
Or
So
can it be either?
it can be either, because what's happening is when a neutron hits 235, it becomes 236. So if you've already got 236, it's going to decay through. If you're creating 236, it's going to decay through. So it really is.
Okay.
These cooling rods, then, actually, I think I've got a picture of the schematic out here. So these cooling rods are how we control reactions in nuclear power plants. Here, for example, if you lower the cooling rods in a long ways, they're going to absorb a lot of the neutrons and slow down your reaction. If you pull them out, you don't absorb as many neutrons and your reaction goes quicker as it goes through. So this is how they control how much energy is released from a nuclear power plant. This is also the problem with our design of nuclear power plants. All 3 accidents of nuclear power plants that have occurred, there's been 3 in history, have occurred because we've lost control of the cooling rods. We wanted the cooling rods to go down, to slow down the reaction or stop the reaction, and for whatever reason they didn't go down. Okay? So therefore we can't control it anymore, the reaction runs out of control, and as it goes out of control you basically have a bomb sitting there. The first, let's see, I've got the 3 accidents. 3 Mile Island was the first one. 3 Mile Island is in the United States. This was a very small one, a partial meltdown. It didn't get really out of control and it didn't spread radioactive material all over the place. Chernobyl was a huge accident. It's basically the top of the scale. In worldwide accidents, everything's just compared to Chernobyl. Like, was it anywhere near as bad as that? Okay, good, it wasn't. Okay, this is the end all, be all. Radioactive material from Chernobyl, when it exploded, went into the atmosphere. And to this day, you can actually find radioactive debris from that accident everywhere on Earth. The atmosphere has moved it to every single place on Earth, and you can find the residue of that accident everywhere. When we looked at the very beginning, and all of us were exposed a small amount to nuclear power plant accidents and so forth, that's where that radiation's coming from. Just this week, they started putting a new dome over Chernobyl to try and keep most of that radiation in and so forth now, and limit the spread of it. This is the Japanese one, Fukushima, from 2011. This one, the cooling rods failed. It wasn't completely mechanical. It was basically the forces of nature were against it. They had an earthquake and a tsunami occurring at the same time at the power plant, and they lost control of it. The enclosure around the source held, but water got into it, and water was able to carry some radioactive debris out of it. So it wasn't spread through the air, it was spread more through a water source in that accident. But all of these occurred due to cooling rods. Just for comparison, there's about 450 nuclear power plants in the world right now. So 3 accidents over the history of these, and about 450 of them are running currently. So there's not very many, but the problem is when there is an accident, it is such a big deal that you can't just ignore it. I mean, if a coal plant burns or something, it's tragic, it's bad and stuff, but it's not a worldwide event. Where when Fukushima had their meltdown, Germany said, we're done with nuclear power. We're just not going to use it anymore. They actually backed away from that and then very quickly said, yeah, we're going to keep using it because of it. So, there you go.
So when did
Yeah.
you say, or how does a chain reaction occur?
So a chain reaction occurs because when uranium breaks apart, neutrons are released, and those neutrons can then react with more uranium to continue your reaction forward. And that's called a chain reaction. I want to tell you, there was a Keanu Reeves movie called Chain Reaction. They were trying to make nuclear power in that one too. There was a time period, nuclear power was really popular in the movies. There were several of them made all at once. So, okay. Any other questions? So about 20% of the energy in the United States comes from nuclear power. And we have a relatively low amount of nuclear power in the United States because we have a lot of coal and fossil fuels available. It's very easy for us to get fossil fuels, so we never really had to rely much on nuclear energy. Other countries, though, do rely a lot in terms of their power generation on nuclear energy. The northern Scandinavian countries actually have quite a bit. Japan has quite a bit as well. Some, I think, maybe France is up to like 40%, something like that. So it kind of depends on where you are and what natural resources are available to you. Now, a nuclear power plant really doesn't differ that much from a traditional power plant. The only real difference is how the energy and heat is created to make the steam. So in a nuclear power plant, you've got what's called the reactor building, and this is a building completely enclosed that has all the radioactive material inside of it. If, heaven forbid, a meltdown occurs, this radiation building is supposed to protect it from the radioactive material being spread over distances and so forth. That hasn't happened all that much in terms of our meltdowns and so forth. But that's the idea. So what's happening here is, right here is our nuclear reaction is creating energy. That energy is being converted into steam by heating up water. And then the steam turns turbines that creates the electricity. So nuclear power creates steam. Steam then creates electricity. In a coal power plant, for comparison, we burn coal, and that gives the energy to create the steam. So the difference really is just where that energy is coming from. One of them is from burning coal, and then the other one is from our nuclear source within it. So we have our elements, our nuclear elements here undergoing it. It's transferring the energy either through an oil or water to a water source, creating steam, and then that's turning your turbines. This is one reason why nuclear power plants are almost always built next to water sources, because they need to bring water in to create the steam to turn the turbines and so forth. So they need a constant supply of water. Yeah.
So this whole process, like when you drive past, like, I guess nuclear power plants, that is stuff that's coming out of the tubes, the steam.
Yeah, so in a nuclear power plant, the stuff coming out of the chimneys is going to be steam.
Oh.
Yep.
So, but that stuff is deadly to the environment, right?
Well, the steam itself is not, except for the heat. The heat, it's going to be really hot because it's steam. But generally, that's going to disperse relatively quickly. So one way you can tell the difference between steam and smoke is steam is going to like disappear. It breaks apart really quickly, where smoke kind of holds together. So from that point of view, nuclear power plant is much less destructive than coal because it's not outputting particles and smoke and stuff like that. But this heat source is actually a real problem. This is one of the major issues that nuclear power plants have, because what they're doing is they siphon water off of a river, and that's got a certain temperature associated with it. Then it's going through the power plant, and it's getting converted to steam and then back to water, but it's going to be warm. The water is going to warm because it's going to heat up some of that energy, and then it goes back in the stream. So rivers, for example, along a nuclear power plant, sometimes above and below the plant will have difference in water temperatures of several degrees. You may have 4 or 5 degrees difference in your water temperature between the two different things. And if you're a fish, that's actually a really, really big deal, right? Where one part is good for your environment and then the other part's bad just due to the temperature changes. So a lot of environmental people raise concerns about nuclear power plants, not because of greenhouse gases, because they're not creating it, but not because of waste and things like that, but because of this issue with the water and changing the aquatic conditions that animals live in and so forth. So I mean, within a few hundred feet, you could have several degree temperature change in your water flow because of that. And that's one thing that's of concern now. This is just a photograph of cooling rods. This is not artificially colored or anything, But what we do with cooling rods when they're done, when they've absorbed all the neutrons, is we store them in water, and the neutrons actually escape back out. And when the neutrons interact with water, it glows blue. So there's what it looks like. Nobody would ever be allowed inside of this room. The radiation levels would be astronomically high because there's constantly neutrons coming off, but it's just a photograph. Yep.
So even with the cooling rods, there's an issue with how you're gonna properly dispose of that at some point.
Yeah, so what they do actually is they they put them in water and then they release the neutrons out. And once the neutrons are released back out, they can reuse them. And that's what they do. Now, the neutrons are being captured by the water. Some are escaping and then dispersing by running into stuff. But yeah, there is absolutely something you gotta do with them.
So the rods control how much energy goes out, but yet you still have to figure out what you're gonna ultimately do with is it the byproduct? Is it the water itself that you would have to dispose of?
The water itself you would have to dispose of and do something with. And then the real thing that we hear about, the nuclear waste that we hear about, that's the daughter products that are coming out. So when uranium reacts, it creates all these daughter products that are radioactive, and that we've got to dispose of in some way. So, yep. Okay. Now, in the United States, all of this stuff is controlled by the Nuclear Regulatory Commission. There are about 100 nuclear power plants in the United States. They're owned really by a small handful of companies, the largest of which is TVA, the Tennessee Valley Authority, which is in the southeast for the most part, but they have several nuclear power sites that they use for the creation of electricity. You can go to the nrc.gov website and find out everything you ever wanted to know about any of these nuclear power sites. If they ever get a fine or they ever have any incident at all, it's there for you to look up. All the safety history, the setup, everything about them is available for you at the NRC. Because they really do want people to feel relatively safe around these things. So they have a lot of rules and regulations on what they share with everyone through their site. Yeah. So for example, here is the location of all of the different nuclear power sites in the United States. These are the commercial ones, not university or something like that. But there you go. A lot of them are obviously on the East Coast. There's a huge amount right there for whatever reason it looks like. This one right here is right outside the town I did my undergrad in. Just 5 miles outside of town. Some of the people I went to undergrad with worked there over the years. I always imagine, you guys remember Simpsons? Homer Simpson worked at a nuclear power plant. I always imagine that's what it was like, but I don't think it was. So there you go. That's that one. Not a lot out here in the coast for whatever reason. But yeah.
What's the colors in the page?
You know what? I don't know. It must be the different regions.
It tells you on there.
It does?
Yeah. If you look.
Oh, I see the keys, okay.
Yeah.
I guess it's the numbers, but
Yeah.
it's not the.
My guess is that if it's the different regions of oversight, but I don't know that for sure.
Chicago just seems like it's a good place.
Well, or they've got a lot of energy.
A quick question.
Yeah,
So are you familiar with Cincinnati at all?
a little bit.
So wait,
Lived
there's
here
only
10 years.
2 power plants in Ohio?
Yes, 2 nuclear power plants
You
in
know where
Ohio.
they're at.
What?
So wait, what's the difference between, wait, I don't know, I could have sworn there was like 6, I don't know.
Okay, so there are coal power plants where they're burning coal to create the heat and energy. But in terms of nuclear power plants, there are only 2. Now, a lot of people remember back the one just in Indiana across the river. There was a plan to convert that to a nuclear power plant, but it was never done.
Do you know where these are at in Ohio?
So, yeah, I do actually. You're just leading me right through my slides today. So one's 21 miles outside Toledo, and then one's 7 miles. I don't know where Painesville is, but they're both on the northern part from the picture there. But there are the two nuclear power plants in Ohio. You see there the steam coming out the tops from the cooling process and so forth. Now, one important thing I do want to mention about that I didn't mention earlier is anything that's exposed to radiation is not released. So, for example, the water that's directly heated by the radiation, that's all enclosed in the power plant, that's not released. They bring in another second source of water to turn into steam and so forth. So that is what we're seeing here. This steam and water was not inside the radioactive part. It's just heat transfer water to water to do that. So there are 2 in Ohio, none in Kentucky or Indiana, 3 in Tennessee. The ones in Tennessee are owned by TGA.
So do they recycle the water then?
So what happens is you have your nuclear source, that heat is transferred by some liquid. That liquid then interacts with water to turn into steam.
Okay.
Now that steam is actually usually converted back to water by another water source. And that other water source is what you're seeing coming out the chimneys.
Okay.
So the stuff that actually turns the turbine is not released, but you've got to cool that steam back into water.
Yeah.
And the easiest way to do that is by interacting it with other water to do that. And that was the stuff that comes off the river and goes out.
Okay.
Yeah.
I remember a neighbor of my parents' house, there was a place in Cincinnati called Fernald. It actually closed in 1989. They actually, they said millions of pounds of uranium dust was emitted in the, I guess.
That was an enrichment site.
Okay.
So they were purifying uranium at that place. They weren't actually like using it. They
Right.
were taking uranium and then purifying it for whatever use there was. Yeah, that's actually a really big deal because a lot of people got really, really sick
One of our neighbors got,
because of that.
yeah.
Yeah. Historically, people who worked at purifying uranium did not exactly get the best health care or anything like that, so they oftentimes had traumatic expenses because of it. So, yeah. Kind of makes me sad. Okay. So those are the power plants. As I said, there's about 100 in the United States. Now, all of this is really the same thing as nuclear weapons. A nuclear weapon is basically a mobile power plant where you release the energy quickly. Here is a schematic or picture, if you will, of how many nuclear weapons there are in the world, we predict. So the United States has about 7,000. Okay? This is significantly down from the maximum. I think maybe this is like, maybe this is, since their peak, shrunk over 2/3. So this is like a third of what there was once upon a time. So that would mean like 20,000 nuclear weapons. I grew up during the arms race, and I remember numerous times as a kid thinking to myself, why? Okay. There is literally one bomb that Russia had that if it was ever set off at its maximum capacity would destroy the world. Okay. It wouldn't split it in half or something, but it would put enough debris into the air that it would block out the sun, and it would basically destroy everything on the earth as we know it. Okay? That's one bomb. Okay? We have like 7,000 for the United States. I guess I understand having a backup, but that seems a bit extreme. Okay? Growing up in the arms race, we always wanted to have more bombs than Russia or the Soviet Union did, but it kind of got out of control very quickly. So here are the estimates for what's in the world right now, 7,000 for the US and Russia, more or less. And then it takes this huge drop down for other countries. France, China, and UK, these 5 countries here are the ones who can make a nuclear weapon on their own. They can enrich the uranium, they can put it together, they can do everything they want to actually create the bomb. The other ones, Pakistan, India, Israel, actually I should add to that, North Korea can make a bomb, supposedly at this point as well. The other ones, Pakistan, India, Israel, those have been given bombs by other countries, named mostly the United States, in terms of what's going on in the world.
So if they set it off, won't they die too?
Well, the deterrent is, okay, so there are smaller bombs than the world-ending bomb. And I gotta assume the thought there is that they could set off the bomb and destroy a smaller area than the world. 2 nuclear weapons have been set off historically, both in Japan by the United States. And in grand schemes of the things we're talking about nowadays, those were tiny, tiny things. But, I mean, I'll show a slide here in a minute. It's like 50 or 500,000 people died from one of those bombs. So, you know, that's unbelievable in terms of what that is. And that was almost 100 years ago, or 80 years ago or something like that. And you can just imagine how much the technology has advanced and so forth. This is one reason why the whole North Korea thing is such a big deal right now in our world. If they're able to create nuclear weapons and actually deliver them, that's going to change their standing. Whether you're pro-North Korea, anti-North Korea, that doesn't matter. It's going to change their standing in the world dramatically. Yeah.
Is there some concern that if like say a terrorist state were to have one of these and they, I guess they don't, some people don't
Yeah.
care if they die, they just take everybody out? I mean,
Oh, absolutely. Absolutely. Well, you see it in movies and stuff, but forget about fiction. In real life, people are very, very, very concerned that a terrorist state is going to get a hold of a nuclear weapon or radioactive debris, because you can do almost the same thing there on a smaller scale, from Russia and the breakaway republics of Russia. That used to be in the Soviet Union, and then when they broke away, they had bombs there, and then what's happened to those over the years and stuff. Security of those types of things is a huge, huge issue. Yeah, I mean, absolutely, people are worried about that. But it doesn't have to necessarily be a terrorist state. I mean, it could be a random person somewhere gets a hold of, yeah. I mean, so who knows? So these are out there in the world, and we need to deal with them and so forth. The idea for a long time was to dispose of them. That has been put on pause recently with the cooling of relations between the US and Russia. I believe that they put that destruction of those on pause. So what makes the weapon? Well, really what makes a weapon is the quick release of uncontrolled energy. You want that energy out, you want it as quickly as possible. To do this, you must have pure material, and this means that you need 90% plus in terms of your purity. So enriching uranium is really, really important here, and that's how the world controls who has the material to make these types of things. Enriched uranium at this level has a name. It's called yellow cake uranium because it's got a yellowish color to it, and it's one of the most controlled substances in the world. We've literally gone to war as a country because we believed another country had yellow cake uranium, and we didn't want them to have that. Right? It's a huge issue. Now, in terms of political realms, obviously this is not a politics class, but if you look at the permanent members of the UN Security Council, they are China, France, Russia, United Kingdoms, and the United States. Those are the permanent members of the Security Council that basically, I wouldn't say the head of the UN, but the subset of the UN that makes a lot of the important decisions. Those countries are all the ones who can make nuclear weapons. So what does that mean? Does that mean if North Korea can make nuclear weapons, they should get a seat as a permanent member on the Security Council? Someone's going to have to decide that. Okay, what if North Korea demands a seat and says, yeah, we've got nuclear weapons, we'll set one off if we don't get one? What's the world going to do? I don't know. I don't have any idea. So it's not pure accident that the permanent seats are those countries. Those were the countries that were most important when the UN was being made. Nowadays, as it turns out, it works out relatively nicely because China and Russia kind of pair up, and then France, the United Kingdoms, and the United States kind of pair up, and they check and balance each other so that nobody goes crazy in terms of various decrees and so forth. Okay, so the story of nuclear weapons starts with what's called the Manhattan Project. And the Manhattan Project was not purely in Manhattan or anything. It started there, but it spread throughout the entire United States. All of the places on this map had something to do with the Manhattan Project. Now, no one place knew every part of it. So the idea was to develop the technology needed to make a nuclear weapon. So for example, in Chicago, this is where they figured out how to create a chain reaction. Oak Ridge here is where they enriched the uranium and purified it. Los Alamos is where they put the bomb together. Project Trinity is where they set it off. Ames, which is where I grew up, there they figured out how to separate the uranium. So all these different places had different pieces that they worked on, but nobody knew the whole scope of things. The project was so secretive, it said that the vice president at the time didn't know about it. The president knew everything, but the vice president didn't know about it at the time. There were really 3, maybe 4 people who would have known the whole scope of things. And the reason it came about was because people were escaping from Germany, scientists were escaping from Germany, and they were telling scientists here in the United States about this new weapon that Germany was trying to make. They were trying to harness the energy of the atom and create this new destructive weapon. So the scientists in the United States, largely headed up by Albert Einstein, went to the president and said, hey, you cannot allow Germany to get a hold of this weapon first because of what they would do with it. So the United States went completely in on this to create a nuclear weapon associated with it. At the time, I firmly believe scientists did not understand what they were doing. They figured out how to make this bomb go off, but they had no idea of what they were actually doing. As an example of this, when the first nuclear weapon was set off, the scientists wanted to see it. I mean, you worked so hard on this, you want to see it, right? So they literally dug a trench that was maybe a mile or 2 away from the blast site, and they sat in the trench to watch this bomb go off. Okay? Their safety precautions were to wear goggles. Okay? Because of this, almost everybody that was there had huge amounts of radiation exposure and caused issues with their health going forward because of it. They just didn't understand what it was. They knew it was going to be destructive and so forth, but no one understood. Where I grew up in Ames, there is a building where they did this work at, and on the roof of the building, they have hinges on the side. And their idea was, okay, well, if there's accidentally a nuclear explosion, we'll make the building so that the roof opens up, it folds open, and then the blast will go up in the sky and everyone will be fine. Okay. That was their thought at the time, let alone what actually occurred from it. So the US worked on this all over the place. We don't have enough time to really get into that. But 2 nuclear bombs were set off over Japan. We can get into arguments about the philosophical nature of this. I don't think it was, you could argue that it was right to set off the bombs or wrong to set off the bombs. There's too many pros and cons for both of them. I personally believe there was no reason to set off 2 of them, but they did. So here is a photograph of the Fat Man detonation, one of the 2 bombs. This one was dropped on Nagasaki, 1945. I just learned yesterday, actually, that the gentleman who took this photo is from this area. His cousin was in class yesterday. So she's like, yeah, I know him. He was the only guy who was present for the dropping of both bombs, actually. And he took photographs of both of them from the plane. So they dropped it, they were flying away, and this is a photograph out of the back of the plane, actually, is what we're looking at. And this is the mushroom cloud that forms. But what a mushroom cloud really is, all of the stuff you're seeing is debris from the ground that's being sucked up into a column of air. the air at the detonation site heats up so much that it goes upwards and then sucks everything in behind it. And that's what you see as your mushroom cloud. All that material gets sucked in and shot up into space, and then it curls over to create the mushroom shape. So when this bomb was set off, it was roughly equal to 22,000 tons of explosives. We now have bombs that are more than 500 times larger than this. This bomb, it was approximately killed about 70,000 people. The other one that we set off, so the other one is called Little Boy. Okay, when it was detonated, we believe that the air became about 300,000 degrees at the site detonation. And when air is hot, right, it goes up. And that's what creates this vacuum and sucks everything in. There were 440 meters per second winds. Radioactive debris came down from the sky for over an hour afterwards. This was really what killed the most people, this radioactive debris. People inhaled it, it got inside their body, and then they had radiation poisoning because of it. Anything made out of glass melted. Anything that could burn instantly turned to ash. It's approximately 140,000 people died on detonation of this bomb, where another 350,000 needed medical treatment. Most of those people ended up passing away from radiation damage. Okay? Add those two numbers up, you get a very, very large number. The US did not just drop it in a random place. They did actually think about minimizing casualties and so forth, but that's a pretty small statement when you look at numbers like that.
Would it be determined if it was even worth it?
I don't know. We don't have time to get into whether it was worth it or not, but the idea of ending the war quickly versus a long drawn-out war, that's really where the argument comes into. So here, very quickly, a photograph. There are photographs online. These photographs were taken by the Army after the bomb was dropped. Now, if you're going to go look for these, I will warn you they are gruesome. Right? Just thinking about what they are is very, very bad. This one is relatively mild. So this is a photo of the city. You'll notice your waterway here, all the houses and everything. And then if we take a look at what it looks like after the bomb was detonated, this is what it looks like afterwards. You may think, okay, they're just super high in space. That's not the case. Here is a building. Here is one of those buildings. Everything else is just completely flattened and destroyed throughout it. So you can imagine what kind of destructive force that is. Now, imagine we go forward to today's date where you have bombs that are 500 times more destructive than this. We need to understand that force, okay, as a people. And hopefully never, ever, ever consider doing this again because of that. So that's the idea there. Comments, questions? No? It's kind of a downer to end on. The very last thing I want to say is, actually, just to give you more of a definition, the nuclear fusion I already mentioned, but nuclear fusion is the opposite of fission. Fission is where you take a large atom and break it into smaller pieces. Fusion is where you take small atoms and combine them to form larger ones. Okay, so that's the idea behind fusion. Hydrogen is a prime example of this. If you take 4 hydrogen atoms, you can actually create a helium. And energy is released in this process. 1 gram of hydrogen would roughly be the same as 20 tons of coal. So you can very, very quickly see how this would be a good energy source, especially when the byproduct to this process is just helium gas. And helium would just leave the atmosphere. So this is why people want fusion in a big way. Yeah?
There's a random question. I remember once you talked about how helium is like becoming more
Rare.
scarce or whatever. Why don't we use this to drink?
Okay, so the problem with nuclear fusion is it's very, very difficult to do. And it takes huge amounts of energy to cause nuclear fusion. So there are actually nuclear bombs that are based on fusion. But just for your knowledge and comparison, the way that they get the energy to start the fusion reaction is they set off a fission reaction first. So they set off a nuclear bomb to cause the nuclear bomb to go off. So it just takes an astronomically large amount of energy, and because of that, it's not worth it in the process to be creating helium. It just takes so much more energy than it's worth. So that's the idea there in terms of that. Yeah, just the cost of the energy kind of outweighs the benefit there, at least at this point. If we don't have any helium left at all, maybe we'll reconsider that. Anything else? Okay. So we are at the end of the lecture here. I'm not going to worry about that. Very quickly, some major topics for you to review for the exam. The idea of background radiation and man-made radiation. And then the idea that background is always around us and so forth along those lines. The general definitions of radiation would be good to know as well. Nuclear equations, the three types of radiation being alpha, beta, and gamma. Then we talked about half-life and the concept of carbon dating as well. Penetrating power was after that. The idea that different types of radiation takes different types of shielding to protect us from it, and so forth. And then we went into applications. The two primary applications that we talked about was medical applications. So look over both diagnostic and therapeutic applications of medicine, and then nuclear power and nuclear weapons. Okay, so those are what the application ones are primarily going to be based on.